Yes. Sorry.
Let me share my screen again.
Perfect. Oh, sorry. Just for my context, then we're saying that what we're going into now is the ridge regression. That's where we're going. That's what's
Ridge and lasso.
ridge and lasso. Okay. Yeah, we didn't learn lasso in class, but that'll be
Okay. I want to do both and do a comparison between these two so that you understand what's the difference.
awesome. Awesome.
Okay. So now, so basically, Ridge and lasso differs only in the aspect of how you choose this function beta.
Got it.
Okay.
Because
And it's
SST is
very,
coming from the linear regression then, so that's not changing then.
yeah, yeah. The SSA is coming from linear regression, so I'll just write it by lambda. Okay.
Nice. Okay.
So for ridge regression,
Is that gamma? That's lambda, right? That
that's
symbol?
lambda.
That's
Yes.
lambda.
So for ridge regression, I'm defining lambda of beta equals sorry, lambda times norm of beta square.
Yes. Cool.
Okay. And for lasso, lambda of beta, which is sorry, mm, this basically means this is the L1 norm
Yes,
which
I
I
remember
talked about.
he taught us the L1, L2 norm, so I know what that is now also.
Yes. So this is absolute value of beta. Okay. It's good to specify this exactly so that we can also talk about how it looks, right? Like how the minimization will work.
And
So
he
in
also
this case, it is,
defined these as the lambda being the hyperparameter here then that we're
yes, yes. So we have two questions. How do you choose the lambda and how do you do the min, right?
what was the second thing you said?
So
How to choose the lambda and?
how do you do the minimization problem? So you have to still solve the minimization, right?
Yes, yes.
For least squares, we had a formula. It turns out the regression also has a formula and lasso doesn't have a formula.
Okay.
Okay. So for lasso, it's still a convex problem.
It's still a convex problem. So you're still taking derivatives.
No, you don't take derivatives because you have absolute values, which is the problem for the derivative part.
Okay.
So you apply some techniques which you probably never have to implement yourself, but all this NumPy and SciPy, these things already have those ways to minimize it for L1 norm.
Got it. Okay.
But it's like a derivative-based minimization algorithm.
Okay.
Okay. And there are two comments. One is the ultimate beta that you choose will depend on lambda.
Yes. Yes.
So choosing a good lambda is important.
Yes.
So the hyperparameter really matters.
Got it.
Okay. So let's do the algebra for each first, and then we'll discuss lasso. So for each L is remember we had this expression for sum of squares of error here, which is this. And then I will have a plus lambda times beta transpose beta. So that's another way of writing the sum of squares of beta is. Make sense?
Yes.
Okay. Now the algebra will look very similar. So I'll just write down the answer or write down the line before the answer. So taking derivative, setting to 0, we get this. Uh, so we had x transpose x. Sorry. Uh,
This is
which,
just simplifying the loss function then.
yes, this is just they're taking derivative of the loss function and setting to zero.
Oh, yes.
So without the lambda term, we had this x transpose x beta equals x transpose y.
Yes.
Now we'll have x transpose x plus lambda times identity.
We're sorry, what are we taking the derivative with respect to? We're taking
The L, we are taking derivative with respect to beta.
with respect to beta. Okay. Okay.
Okay. And then we end up having something like this. X transpose x plus lambda I times beta equals x transpose y.
Oh,
So that's where lambda appears. And then your solution for beta reach is x transpose x
inverse
plus
lambda I inverse
whole inverse and then
times X transpose
x
Y.
transpose y.
Very cool.
Okay. Make sense?
Yes.
Okay. Good. So remember we derived this thing, your hat matrix in terms of this PP transpose, right?
Yes.
Okay. We can do similar derivations here also. So we remember we had x transpose x is q d square q transpose.
Yes.
So I will use this fact now.
Oh, nice.
So I will show you how the whole algebra changes. So the first thing is inside the parenthesis we have x transpose x plus uh, lambda I. So it will be this plus lambda I, which I can write as q. So it will be like this, but instead of d square, it will be d square plus lambda I.
Very cool.
Okay.
Yes.
And the magic is happening is q and all this will remain. So let me just write down the expressions. Uh, so, okay, fine. So once you have this, let's not get remove it. So we have beta reach. We'll have this x transpose x whole plus lambda I whole inverse. So that will have this thing, but this part will get an inverse first of all. Mm.
Oops.
Yeah, I'm not sure what happened here. That's not- it's pretty good. Yeah, typing all this is a huge pain.
You're very fast at it though.
I mean, it's very slow. I mean, I can appreciate profs who teach based on a PowerPoint presentation because there's no way a teacher will type all these things and like do either they use Blackboard or do PowerPoint.
Yeah, now they have
There's
the
no in between.
iPad. They're doing the iPad where,
Yeah, nowadays they will, which is like a Blackboard kind of thing.
yeah, exactly.
It's just whiteboard. Yes. So we have this thing, and then you have X transpose, which will give you Q, D, P transpose, and then you have Y.
Whoa.
Now, if we look at this, we'll have a simplification here. This Q transpose Q will cancel out.
Identity there.
So we'll be left with I'll just remove this part. Yeah.
Okay.
Now you see that you have d square in the d square plus lambda I in the denominator and d. So the individual elements are, so if let's say you have a di, which will be divided by di square plus lambda. Now suppose your di was very small, which is the situation we talked about. So if di is very small, without the lambda, you have 1 over di, which will be large. Okay. So suppose I fix lambda to be 1. Now, if my di is actually large, let's say 100, then it will be 100 over 100 square plus 1. 100 square plus 1 is almost 100
Hmm.
square. That plus 1 will not do anything there.
Doesn't matter too
So the
much.
value will be very close to 1 over di. So for large di, this is close to 1 over di. And then for very small di, the opposite thing will have. Because the di square is very small. If di is small, di square is even smaller. So the lambda will dominate. So di over lambda.
Can you define DI again? What is DI?
Di is the singular value. So D is the diagonal matrix of singular values, right?
Okay, so
And
that,
we discussed what happens if the some singular values are small and some are large.
yes, okay,
So now we are showing that for large singular values, this is 1 over di, and the lambda doesn't have any effect. So the large singular values are not affected by the lambda parameter, which is a good thing. We don't want the large singular values to change. We only want the problem was the small singular values.
got it,
So the small singular values are adjusted by something like this. Instead of 1 over di, we are getting di over lambda.
got it.
So if di is small, then this quantity will also be small.
Yes. No, if DI
So
is
the
small, that quantity, if DI is small, that quantity will be small. Yes,
that
sorry.
quantity will be small. So if di is large, 1 over di is small.
DI is large, 1 over DI is small. Yes.
And if di is small, then this quantity is small.
That quantity is small. So that works.
So that means I have, yeah, that works. That means in either side, I have kept the quantity small, and this
Oh,
will, my
cool.
variance will be small.
Oh, very cool.
This is the magic.
Cool, super cool.
Okay.
So that right, the that is important then the DI over DI squared plus
Di
lambda.
square plus lambda. Yes. That is what is changing things. And the variance term will be, so earlier we had q d power minus 2 q transpose, right? This one.
Yes.
So it will be same thing except that d square, d power minus 2 will have that plus lambda kind of thing.
Yes. Into inside of there.
In,
Yeah.
yes. So it will be d square.
Plus lambda I plus.
Yes, and then minus 1. I don't know why the minus 1 is not working good.
This is so cool.
Something.
Okay.
So that means the small di's are getting an adjustment of lambda. The large di's are not getting affected much.
Got it.
Okay, so we are correcting only the small singular values, which is what we wanted to do. Okay. When people do these kind of things, they talk about something called condition numbers, which is defined as the ratio of the largest to smallest singular value. So because the singular values, like instead of thinking about absolute values, you think about how much smaller or larger they are with respect to each other. Like if the largest value is 100 and the smallest is 0.1, then the ratio is 1000.
One sec. Sorry, CJ.
Yes.
What I was expecting though, maybe this is a dumb question, but I was expecting that we're trying to find some formula for lambda. So what I was expecting at the end is like lambda equals something, right?
Okay. Yes.
Because that's what we're solving for, right? So,
No, we're solving for beta. We found a formula for beta here. So this one is the formula for beta.
but we don't know but how do we know what our lambda is? I thought we were trying to figure
Yes.
that out.
So no. So there are two questions that we discussed. How do you choose the lambda? Lambda is something to be chosen, not solved. It's a
Okay,
hyperparameter. So parameters are solved,
right.
hyperparameters are chosen.
Right.
Okay. So for example, when you do sampling, what's the sample size? That's not something to be solved. So sample size is chosen.
Right.
And then for that sample, you can solve for something and all that.
Got it. Okay.
that kind of idea. So we still need to find a way to choose a good lambda. So I will come to that. But once you have chosen lambda, how the lambda is affecting the net result is what we're discussing at
That
this point.
makes
Okay.
sense. Okay,
Yeah.
I got you. So now we
Okay.
have a formula for the beta and we have a formula for the variance as well then too. Okay.
Yeah. So that means
Sorry,
and
there's supposed
we
to
have
be equal to sign or something there. The variance term will be,
okay, yeah, I can put in full sign.
oh, wait, what? How are you defining variance with variance in there?
No, the sigma square is the variance of the error. Standard is the variance of the error. This is variance of the beta hat.
Got it. Sorry. Okay, okay.
This quantity, like we derived last time, right?
Oh,
The
yes,
variance of
yes,
beta hat
yes,
LS.
yes. Sorry.
Yeah.
Yes. Okay, I'm with you. I'm with you.
Okay. Yeah. So that's what it is.
Okay.
And actually check this algebra. This might be slightly different from this also. But this is the main term and there might be some extra plus something smaller terms.
Okay.
I'll check that later. But this is the idea is that we are making the very small diagonal elements to be larger. So and one way to like mathematically express that is the condition number, which is the ratio of the largest to smallest. So suppose earlier it was 100 versus 0.1. So the ratio was 10,000, right?
Okay.
And then that actually gets squared because we have a d square.
Right.
Squared will give me 10 power 6. Okay.
Okay.
So now let
Condition number.
lambda is 1. Just I'm choosing some number.
Okay.
So now the 100 will become 101. Sorry, 100 square will become 100 square plus 1.
Plus one.
Square plus 1
Right.
divided by 0.1 square plus 1. Okay.
Okay.
Now you can see in the numerator it is 100 square, which is 10 power 4. And
Right.
denominator this 0.1 square will be near to 0. So denominator is just 1. So now my condition number will be 10 power 4.
Yes. Oh, that's supposed to be a squared,
Square
right?
of the condition number, yes. So it was earlier 10 power 6. I have improved it to 10 power 4.
Yes.
Okay.
Sorry, the zero, it's supposed to be, I think, right? 0.1 to the power of 2 there. Yeah.
Yes, sorry.
Okay. Perfect. Yes.
Let's do another value. Lambda equals 10 instead of 1.
Okay.
So
Okay.
then I will be left with 100 square
Oh,
plus
interesting.
1.
Plus 10.
Then,
Oh,
sorry, 100 square plus 10
yeah. Plus
divided by
divided by 0.
0.1 square plus 10.
Right. So 10 power.
Now, so the numerator will have 10 power 4 plus 10. Denominator, I'm ignoring the 0.1 square, so it will be just 10.
Yeah.
So I'll be left with 10 power 4 plus 10 divided by 10, which is 10 for
Power 3.
10 power 3000 plus 1.
That was plus 1.
So,
Okay.
yeah.
Got it.
So instead of 10,000, we have reduced it to 1,001, much smaller.
Yes.
So it was originally 10 power 6. Now it went to 10 power 4 and then 10 square,
Got
10 cube.
it. Okay.
So you can see how it is improving.
Got
So
it.
the larger the lambda used, the condition number will improve.
Ah.
If you put your lambda to be close to infinity, then our condition number will be close to 1.
So we're looking for that condition number to be small then.
Uh, yes, we are looking for condition number to be small.
So why don't we, are we supposed to set the lambda to like infinity there?
No. So the question is, what's the downside of doing this? The
Oh,
downside is,
I think I know. I think I know.
okay,
Is this
yes,
the bias variance trade-off then?
yes, this is the bias variance trade-off. So
I
we are decreasing the variance, but we are introducing bias by choosing a lambda.
got it.
And you can actually calculate the bias for a given value of lambda and all that. So like we had two results, right? For least square beta, we first say that it is unbiased, and then we said the variance is this much.
Yes.
So now, if the variance is very large, then we are very concerned about this. So we are trying to improve this. But the first part will go worse as a trade-off.
Yes.
And then you can actually do the calculation and see how much the trade-off is, and then choose the best lambda based on that also.
Okay. So Jay, can
What
I
lambda is
suggest
better.
something? Can I
Yes.
suggest something? The bias variance trade-off is a big topic that he keeps emphasizing.
Yes.
Can we do maybe, can we start next session with that?
Yes, we can do that.
I have one more favor for next time also that I want to maybe go through. I know it's going to be some work for you, but
Yes.
I think it would be very helpful for me here. So Jay,
Okay.
I'd like to see a real data set where we do like a ridge regression on with this in Python or something. Maybe if you have like a script with like NumPy or scikit-learn or something like that, just to see how these formulas translate to like a real data set.
Mm, I can try to produce that. I will see if I can do that in the
Even
next
if
session.
it's super simple, just like 10 data points or something like that, it doesn't have to be a large data set or anything. But I'm
Okay.
curious if I'm able to see this and see how the Python relates to it too, I think that'll be super helpful for like all my homeworks and stuff like that.
Yes, sure. I can
So
try to
if for
do that.
next time, maybe
Maybe not by tomorrow, but by next class after that.
are you free tomorrow?
Yeah, I'm free tomorrow otherwise.
Okay, if you're free tomorrow, can we do bias variance trade-off then starting tomorrow?
Yeah, yeah. We can do that tomorrow, but this data set thing might not be ready by tomorrow.
No, no rush on that. No rush on. I have a test in like 4 weeks or something like that. So I
Okay.
have some
Yeah,
homeworks in
yeah.
between
You
and
have some
stuff.
time
But
before that. Yeah.
if we can go through like a real data set with some NumPy scripts or
Yeah,
scikit-learn
yeah,
stuff,
sure.
I think
I
that'll
can
be
produce that.
helpful for me to
Yes,
relate all of these
yes,
formulas into Python then as well too,
yes.
just to see
We can
that
do that.
as
Yeah.
well. So, okay, buddy, I'm gonna say, can we stop here today then? This is a good stopping point for me, I think.
Yes. Uh,
Is there
just
anything
let
else
me.
that I should note theoretically here on
Yes. The other. So I wanted to discuss two things after this. One is, so as we discussed, the bias variance trade-off is one way to choose the lambda.
yes.
So let me just write down. So this is a general question of how do you choose any hyperparameter in any model, and this will keep
Oh,
recurring in every machine learning model.
yes.
So the first is uh, so one way to solve the
Sorry.
bias
Can
variance
I do
trade-off.
something? Can I do something?
Yes.
I'm gonna